Okay, so it's you probably saw something similar to this in the earlier presentation from Michelle, and this is just a reminder of the structure of the OFMF proof of concept tool chain that we're going to use to manage a Gen Z fabric today. So down here on the right-hand side, we have actual hardware. It's brought to us courtesy of IntelliProp. And on the and it's actual hardware. It's running somewhere in Longmont, I believe. Then we have our proof of concept agent code, which is running elsewhere on a VM. We have our OpenFabric management framework proof of concept code that is running on a different virtual machine, pretty much in the same environment as the agent. And then we have a CLI-based admin tool emulator. Since we don't have real admin tools for this, we're doing it all with emulation through basically me running the keyboard. So the two proof of concept stacks over there in the middle talk to each other using Redfish. And the CLI talks to the OFMF proof of concept framework using nothing but Redfish as well. So this is the block diagram of the actual hardware system that we are running. It's not very big, but it is powerful. We have ZMM or Gen Z memory modules. We have compute hosts, which also may export Gen Z memory to the fabric. We have switches. There may be multiple devices. We're only showing one in this block diagram. And we have a Zephyr SoC, which is just another SoC host, but it is running the Zephyr Fabric Manager for Gen Z, which is an open sourced Linux-based application that runs on top of Gen Z capable hardware and acts as the in-band manager of the Gen Z hardware. So all the commands between Zephyr and the hardware travel in-band through the Gen Z fabric. Communications between the Zephyr FM and the admin systems are out of band via Ethernet. And so this is how our software stacks that are applied by that very first slide we talked about map to the hardware. So we have our Zephyr FM running down on the SoC. And then we have the agent. It's a Python proof of concept code running on a virtual machine somewhere. We have the OFMF that is also running on a virtual machine in Python, and it's probably in the same general environment as the agent. And then the CLI is actually another Python stack that is running on the admin system that runs the agent, because I did the code for both of them, or most of it anyway. So all of the layers do communicate with other layers via HTTP RESTful protocols. The OFMF uses only Redfish for its communications with its clients or with its agents. So this is a quick look at how the Redfish represents something like our Gen Z demo system. And it's not perfectly accurate, but it's representative. You can see that we have hardware represented by devices and ports with specifically physical connections between the ports of the devices. That makes up your fabric. So you have fabric adapters, they have ports, they are cabled to switches, which have ports. other ports of the switch cable over to media controllers, and those things are all connected to actual endpoint devices that represent resources to the fabric. And I'm going to deviate a little bit here and point out that not only is Redfish giving us standardized objects that model the fabric components and the resources that appear on the fabric that we want to manage, but it also supplies a standardized structure for locating these resources. So in a little bit, we're going to talk about locating all the memory in the system. And there are several ways to get to all of the memory in the system. And Redfish allows you to pick whichever is most convenient. Today, we will go through from the service route through the chassis on the right to the media controllers, or I'm sorry, we will go to the memory domains, and we will search all of the memory domains for all of the memory. And we will trace back all of the memory domains to the sources of that memory and the endpoints on the fabric that they are presented through. And then you carve the memory domains up into memory chunks, and that's what you assign to various servers to use. And we make those assignments using connections. And so the connections talk about producers and consumers or targets and initiators of traffic. So the systems on the left will be tied through their endpoint to a connection, which will tie you to a memory chunk that you can use. So those are all logical things, and we haven't yet talked about the physical stuff. And in general, when you are managing fabric resources and you are not the fabric manager that does all the routing in the physical fabric, you tend to not show the physical ports.
Russ,
Yeah.
we had a question on this.
Mm-hmm.
In the Redfish tree, why does the Fabric Manager appear as a system instead of a manager within the Redfish schema?
It would. I show it as a system that can also execute code and access resources, um, just so I have a place for it in the simplified version. But it is an endpoint on the fabric and therefore shows up as a system.
Cool. Thank you.
So we have a simple little demo. It's a simple little request. It might not be too easy to satisfy, but I want to find a big chunk of fabric attached memory that two servers can share. And I want to do this as easily as possible and as efficiently as possible for multiple fabrics today and in the future. So my fabric manager, my fabric admin has to find the memory available on the fabric. So we'll go to our memory pools, our memory domains, and search it out. We have to find the servers on the fabric. Then we have to find the free memory that's in the memory pools, and we have to carve a chunk of it out. And this is all very abstract, but the amount of work you have to do for a given fabric might be considerable. And then, of course, we have to decide which two servers to connect to the memory. And once we do that, those two servers are allocated to those bound resources, and we can build protection domains around them and isolate them from access to the free memory or other servers' used memory. And the nice thing about it is it's all done with abstract requests. I can turn around and do a similar problem tomorrow on a different fabric. So the demo today, we have our right-hand side in hardware. We have our agent proof of concept. We have the Ofmf proof of concept. And then we have me playing the part of multiple tools. So we're going to walk our way through the basic fabric agnostic operations that we just discussed in general on the previous slides to do some creation of shared memory regions and then creating connections to those shared memory regions so they can be used. And then we will show you a little bit about two servers using the shared memory. And that'll probably take us out. So the demo. All righty. So are we ready, Eric?
Yep, ready, Russ.
Okay, so what we have here is the Ofmf interface layer or proof of concept as the layer that's interfacing to the clients. In the middle left side window, we have the diagnostics from the agent proof of concept code. And in the very bottom left, we have this simple CLI, and I will warn you, it's very primitive. I am not a Python programmer. I have not written any Python before we did this. And it's not necessarily fat finger proof, so I'm going to go slow. So the first thing we're going to do is just reset the software stack. The hardware is up and running and waiting. We're going to go query the software or query the hardware for all of the resources. And that's what we just did. So we're going to go get all the memory resources. We're going to sort the memory resources. And then we're going to list the memory resources. And this is as pretty as this output's going to get. It's going to get a little uglier because I did not waste any of my time learning how to make Python output in a CLI pretty. I have print statements everywhere, and you're going to see a whole bunch of stuff screaming by. Hopefully it all ends with a successful tag. So we see that we have our 4 devices that are presenting memory to the fabric. And we have the size, and it's actually in bytes because that's easy for me to play with. And these free sections all start at address 0, meaning they're just baseline. I can tell you which endpoint they're on. And we keep track of which fabric they're on because this proof of concept will probably be extended to handle multiple fabrics at some point. So in traversing that Redfish tree, you search fabric by fabric, memory domain by memory domain. And we can also take a look at which systems are available. And there's just too much data that we collect about the systems. So I don't put them in a fancy format. So the first thing we wanted to do was create some memory chunks. So which fabric? Well, there's only one. And here's where I go slow so I don't fat finger something because that can cause problems. And, oh, I don't believe it. For some reason, my link to this system just reset. Give me a second. I will log back in. Everything's still running on the systems.
While we're waiting, there's a question that's come up. What is the granularity of memory slices?
It is hardware dependent, and it is some of the information that is passed into the it's passed into the agent. It's not going to like that. It's passed into the agent, but
So I can, while you're trying to log in, talk to
yeah,
that.
why don't you answer that?
So as Russ mentioned, it is hardware dependent. It depends on how some of the address translation structures were defined in the various hardware components. In our simple fabric that we're showing today, the allocation granularity is 64 megabytes. But yeah, that can go up or down depending on how things are created from a hardware perspective.
Cool. Thank you.
Yeah, and if there's no other questions, I can sort of talk to the setup of the shared memory portion of this demo while Russ is trying to get back in. It
Go
looks
for
like
it.
he's back in. All right, that was fast, Russ.
Yeah, should have been easier. All right, so we want to attach to one of the memory chunks or one of the memory domains and create a chunk. So we're going to go after memory domain 3. And we said that we were going to make this one basically 32 gigabytes. And this is going to be type 2 DAX memory. These are one of the things that you have to explain to your hardware fabric manager. So you have to pass this down through some Redfish property all the way from the admin. Okay, so it's out there. And one of the other things that makes this work well is keep no state in the CLI. Could have restarted the CLI if we'd needed to, and it would have gone out and it would have queried the Ofmf Redfish tree, and it would have come back with the same answer, that there's still 4 memory domains out there. There's still free space in each one, but there is also a allocated chunk of memory on memory domain 1, and that happens to be the 32 gigabytes. Do we want to just try to hook into the 3 systems?
Sure.
So we have no connections, but our next connection ID is going to start at 12 or 13. So let's create a connection. So which fabric? Again, because you might be dealing with more than one. Which memory domain? This is going to be memory domain 3. Which memory chunk? Memory chunk 1. Which system ID? I'm not going to go back and look. I'm just going to tell you that it's we're going to hook up all 3 systems. So the first one is system 1. It's at fabric adapter 1. You might have more than one fabric adapter per system. So that worked. And we can whoops, it's not list. Let's get cons. So it came through as connection 13. I'm writing that down. All right, so we can do another connection. Same fabric, same domain, same chunk, let's tie system 2 to the same fabric, right, or the same chunk. Those two systems are now sharing a chunk of memory. Do you want to break here since we're running a little short on time and go run a quick demo on
Sure.
that?
Yeah.
Okay.
So let me first. So I'm going to take control. Just a quick little background. The right-hand side of Russ's terminal share are SSH'd into 3 different hosts, what we call SOC4, SOC3, and CXL1 at the bottom. I'm just first going to show, if I can type into them. Let me respawn. Okay, first going to show that Russ created a DAX 1.3. So let me respawn this one as well. And same DAX device is going to show up on this host. So just a little quick background of what I'm trying to do here. Now that Russ has created a shared memory chunk between systems 1 and 2, I'm going to run a very simple program that showcases the shared memory use case. And one of the hosts is going to be a writer into that shared memory, and the other one's going to be a reader. I have a FIFO, software FIFO-like control structure that I've placed into the base of the DAX device that's going to manage how data is moved in and out. The writer will increment the input pointer, and the reader will increment the output pointer. I'm going to push in something like 50,000 8-byte objects that are randomly generated. And when I'm doing so, I will be keeping track of a checksum. That checksum I'll output at the end of the push cycle, and then we'll see another checksum on the pop cycle and see that they match. So to start, I just point this SMEM program at the DAX 1.3 device that Russ created. And you can see that's 50,000 packets or objects being pushed in. And here you can see the checksum. So on the other host, SOC3, I'm going to run the same program, but I'm going to run it in read mode. Oops. Okay. And there's the pop cycle. So you can see the checksums here and here match, indicating all the data read out of that shared memory structure was consistent. So it's a very simple program, just showcasing the fact that we can interact with this resource that Russ has handed over to the 2 hosts. This could easily be extended to do more complex things like multi-reader in-memory databases, or even like shared training data between multiple nodes for deep learning use cases, things like this. So if you want to allocate another resource, Russ, maybe to CXL1, that would be good. So if you're talking, Russ, I can't hear you, but fundamentally you're going through the same procedure as you ran before, just with this particular connection will be created on a different memory chunk.
Well, we don't have a different memory chunk at the moment.
Okay, well, let's do the same one.
Okay, so we'll take this memory domain 3 and we'll take chunk 1 and we'll assign it to system 6. And there it's done. You want to create a new chunk? Whoops. Oh, you stole it. Okay.
Yep, I was gonna just show that. Ooh, I need all of my panels needed to get relaunched. I was just gonna show that we have that same DAX device over here. So we could make another chunk. We could interact with these a little bit more. We, I think, only have a few minutes left. If we want to pause here for questions, how do you want to proceed?
I'm happy to.
So we have one question. It's obviously this is a proof of concept, but the question is, what kind of security protocols can you put on the fabrics?
Yeah, so definitely proof of concept. One of the things that you can see in the resource description over here, if I highlight on Russ's screen, the R key. This is a read-only, read-write key that could be provided to build in hardware-enforced isolation between different resources, for example. We're not doing any of that in this POC at this point, but there's some flexibility and security controls that could be implemented in the future.
Yeah, and it's entirely dependent on how you want to structure your fabric management system. You can either put the manager of all of those security details above the Ofmf and pass everything through Redfish, and you have to work within the Redfish protection schemes, or you can make it you can hide that from everything above the Ofmf and make that part of your agent and Ofmf and Zephyr or Fabric Manager layers. So you can put it where you want it. You just need the objects and the control knobs to manipulate them at the level you want to manipulate them.
So you've got about 2 minutes if you'd like to do some more, or we can close out. If there's any more questions, I would love to be able to ask them. Very good demo that went pretty smoothly. Congratulations.
Yeah, getting booted off is the worst thing that goes wrong with a demo. Yeah,
exactly.
I'll take it, particularly one that is hand-driven by CLI.
There you go. Well, hopefully we'll get the graphics user interface for the next time we give this demo.
Yeah, and we'll have hopefully more than one fabric to play with. And
yes, that would be very cool.
Demonstrate the ability to launch the same applications on 2 different fabrics.
Exactly.
Using the same set of commands.
Okay, is there anything else you guys wanted to show?
I don't have anything else. Did you have any other questions?
I do not have any other questions queued up in the chat.
Okay. All right. I am going to stop sharing.
Well, thank you to all 3 of you for doing this today. Appreciate it.
Yes, and thank you to IntelliProp and Jim and Eric for getting the hardware online and leaving it online for me to play with for days.
Well, cool. Okay. Well, thank you guys. And that wraps